Okay. Excellent connection. That's good. Okay. Looks like everyone is happy. Okay. Hello. Welcome to today's stream. We're going to be looking at taking the MicroBlaze, specifically the MicroBlaze RISC-V version, using its AXI-Stream fast simplex link feature to do kind of register access or register to AXI-Stream conversion. And we're going to demonstrate this with kind of a co-processor HLS accelerator. So we're going to try to step through those steps in like 45 minutes to an hour. I am FPGA Zealot. You can watch this on YouTube, Twitch, or LinkedIn. We'll be starting in 4 minutes, but feel free to say hi in the chat. Feel free to talk about why you're here, your interest in FPGAs, RISC-V, HLS, accelerators. If you want to ask any questions, feel free to ask any questions during the live stream. I'll try to interact as best as I can. But feel free to say hi, and we'll start in a few minutes. So, see, watch analytics. Oh, good. Yeah, not bad. Okay, if you are just joining us, we'll be beginning in a few minutes. I mostly just started the stream early to verify multi-stream works, that we have good connections, if there's any issues with audio or video, but feel free to please say hi in the chat. And we're going to be trying to do as close to a live demonstration of Vivado and Vitis that we can. Try to walk through all the steps, and maybe we'll cheat a little bit to get past some compile times. But hopefully you can repeat this on any Vivado supported FPGA. This doesn't use much logic. You can easily use this on a Spartan 7 to a large Vertex or Versal device. The Versal is going to be a little bit harder, and the Zinc and the MP-SOC have a little different variations that might be a little harder to set this up on. But Spartan, Artix, Kintex, Vertex, it should be about the same flow, whether from the Series 7, UltraScale, UltraScale Plus family. So, wait just a little longer, and then we can start. Mic positioned a little bit better. Okay, so I'm going to go ahead and get started. Welcome to the stream. I am FPGA Zealot. We're going to be doing a AMD, I guess, sponsored stream today. We're going to be looking at the Spartan UltraScale Plus FPGA, and we're specifically going to be looking at implementing their MicroBlaze RISC-V soft processor on it, and looking at the AXI-Stream features to be able to do some hardware acceleration with a co-processor HLS accelerator. So let's go over a few details. Disclaimers: I am not employed by AMD, and this is not a paid stream. This is more they lent me the hardware and I'm playing around with it. I do not offer official support for any AMD products or software. Some of the links in the descriptions do provide analytics to AMD. There are no commissions earned. The content in this channel is created for information purposes only, and all opinions expressed on this channel are my own. I am FPGA Zealot. You can find me on YouTube, X, and Twitch. I'm also Andrew Wilson on LinkedIn. And today we'll be looking at the Spartan UltraScale Plus. This is a recent part that's in production. We'll be looking at, we have one of the smaller variants, the SCU35P. This does not include DDR or PCIe or transceivers. This is on their smaller package. But it does have a lot of nice features, and it does include, the UltraScale Plus node process that allows you to get up to speeds like 300, 400 megahertz pretty easily. And if you work on your design, you probably could get up, closer to 600 megahertz. So really powerful, smaller fabric. We have the SCU35 dev board. Mostly going to be inside the FPGA, so we're not really going to be accessing any of the I/O today. This is just the development board we're using. It's mostly just going to be using the JTAG and the UART today. We should look into the future streams. I want to look at the HSIO, and maybe we can look at trying to get Ethernet working as well. But for today, we're just going to be using JTAG and UART. So today, we're going to be just kind of building from scratch and talking a little bit about the MicroBlaze and the MicroBlaze 5 AXI-Stream fast simplex link feature. We're going to create a quick loopback design where it's just going to plug the MicroBlaze back into itself. And then we'll look at adding an accelerator in the AXI-Stream with Vitis HLS. And then we'll do a full demonstration of the system to show you how it works. There's probably better, we're not going to dig too much into HLS today. We're just going to demonstrate how you can generate a AXI-Stream capable HLS. Or there's a lot of interesting features you can dig into the HLS if you want to look at things. I do want to look at doing some more fancier HLX accelerators in the future, probably next month, and we can maybe post about those as a GitHub project or article later. So let's just start from scratch, right? So we're just gonna, this is just gonna be kind of your default 2025.1 Vivado install. We're just going to go do a new project. We're going to do SCU35 dev board, which comes built in. I'm going to do this kind of fast. The previous streams, the first stream on this board, I do dig into a little bit more of what I'm doing when I do the speed run of the MicroBlaze. But today we're just going to look at how do we implement the fast simplex link and we get the AXI-Streams working. So I'm going to start off doing kind of like a generic MicroBlaze design. And then from there, we can add the AXI-Stream capabilities and show how we are going to look at it. So it's mostly going through the same process you normally go through. We're just going to keep this all default. Okay, first thing I like doing is turning off the reset on the clock wizard. I like a free running clock. And then we're just going to use the default. And then for the reset bus, we'll do the reset, look those up. And then the only other thing, we're going to go to the board tab. We're going to add UART-B, plop in an AXI light, hook it up. We're going to go to default kind of processor baud rate, which is 1.5200. And then we're just going to that up. So right here is we have kind of your default RISC-V processor. But now we want to add AXI-Stream capability. We had a comment from YouTube asking about video mixers. I'll be looking at a new kind of project in December that's going to be looking at multiple camera and display streams. So hopefully we can talk about video mixers within the Vivado IP course next month. But yeah, stay tuned. We'll talk about video mixers in the future. Okay, so we're good for the RISC-V. Now let me make this a little bit smaller so it fits in the screen. Okay, so to enable AXI-Stream, we're going to go to the last tab here, 5 out of 5 on the MicroBlaze, and we have a number of stream interfaces. I'm just going to hit 1. And that's going to add M0 AXI-S and S0 AXI-S. And we're going to connect this to an AXI4 stream data FIFO. Drop this down here. We're going to go here. We're going to make it size 16. We're going to force it to distributed RAM, which is going to be very basic FIFO, nothing too complicated. We're going to connect it up to the processor. And it's going to ask for a clock. We'll provide it a clock. We're going to mark these as debug. Then we're just going to hook up an ILA core to them. And here we go. So this is our basic loopback. We'll see if we go interface view, right? We can see what's happening here. No loops. Reduce chunks. And I think that breaks it. Okay, so yeah, we have the master interface going to the FIFO and the coming back into the slave interface. So we're not going to build this right now. I'm going to reopen another project that already has this set up, but we would, next export the hardware and set up a Vitis project. So what we're going to do is we're going to load in the project that's been pre-built. And then we'll get Vitis up as well. I forgot to fix this. I'm supposed to make this easier for everyone to see. Okay, so open up the block diagram again. While we're here, let's go open up the SDK for this. Okay, we got the same design. Here. Okay. So now we're gonna open up our local system. And we have our interface already. Okay, so let's talk about the software. So if you've gone through this before, you import the XSA file, you can deploy a platform, and then build a hello world template. So we're using the put and the get FSL fast simplex link commands. You can find these in this RISC-V interface document. And basically, it's just assembly. It's just a wrapper around some assembly instructions. So we have blocking get, a blocking put. We have non-blocking get, non-blocking put. We have a control. So the control bit is using TLast. So on these interfaces, there is a AXI-Stream TLast. And in the software, that's called the control bit. Right there. So when you do cget and cput, you're checking for that control bit, which is TLast. There's these interruptible versions that I need to look more into. I haven't seen a very good example of them yet. And is valid is going to look at tvalid, or no, yeah, tvalid, and this one's going to look at TLast. So you can check for TLast or tvalid and TLast with these two instructions. But today we are just looking at the basic blocking data read and write, the get FSL and the put FSL. So what we're going to do, since our FIFO is only 16, we're going to, let me make sure that our optimization is 0. I want to show you different optimizations here. So we're going to write 16 values just with the bottom byte and the top byte written. We're going to get those values, stick them in a buffer, and then we're going to print out the buffer after the loop. So let's get the error term over here. So we built this with kind of a basic optimization, and now we can run it. Did trigger? Didn't trigger. Go ahead and fix it. So, oh, actually ran twice. I must have not reprogrammed it. Yeah. Okay. Let's go ahead and reprogram it. I want you guys to see a fresh program. Okay, we're gonna rerun it. Any other questions in the chat? Oh, I forgot the trigger. So we'll go through here, rerun again. I want to look at the trigger, show you the trigger specifically. So we're able to send the data through the FIFO, write it and read it, and we can send multiple values. I just want to show you the timing. The timing is the most important part of this. I forgot to set up the trigger. So we're going to set up the trigger. I want you to look at quickly this does. So a processor can take multiple cycles to do, like a AXI memory map or other commands, but these are directly registered to stream. These are like single cycle actions, so you can do them very fast. But I'll show you the difference in the optimization. So we're triggering the trigger set. Now we're going to just rerun through this again. I just want to show you looking at the spacing of different optimizations for this. Okay, so in the right bus up here, we zoom in. There is, so this happens at 16 and this happens at 37. So there's almost 20 cycles between each write. What about the reads? The reads looks like about 20 cycles as well. 350, 374. Yeah, about 20. That's about 24 cycles. So that's still kind of slow, right? You want this interface, this coprocessor, potentially be faster. And I mean, that's as easy as going into our configuration, going from no optimization to your standard 03 optimization, and we're going to rebuild this. I'm going to reprogram and trigger this. And we're going to trigger. Now with the 03 optimization, I'll run this. See how it goes. Now we look back here, it's much, much tighter. So the optimization is very critical here, right? So it's now every 3 cycles we can do a write, and it's a little bit longer on the read. So it's every 4 cycles on the read, which is 5x faster. So this is a situation where doing optimization can be very critical into how fast the system runs. So that was the basic loopback of just proving out that we can do the AXI-Stream through these 2 loops, right? I'll highlight this. I can. Okay. Any questions? I'll move on to the HLS portion next. So next we're going to look at doing a quick Vitis HLS dot, and we're just going to do a very basic pass through with some different control and status features just to demonstrate how it works. And make sure I open up, yeah, I can open up the other code. So to do HLS, we're going to open up like a whole new workspace. Oh, well, I should say, if you've joined us since we started, I'm FPGA Zealot. We're doing an AMD Spartan stream talking about the MicroBlaze V with the RISC-V soft processor. We're looking at doing AXI-Stream to a co-processor HLS accelerator. Thank you for joining us. Feel free to talk in the chat. Any comments, questions are great. We're now moving on to looking at the HLS portion, and then we'll integrate it with the whole system. So we're going to go ahead and set a new workspace. Let's go to our project we set up, which was this right here. Do folder, call it HLS Gen folder. So now we're going to create an HLS example. So what we're going to do is we're going to the examples right here. We're going to go to HLS examples, go to the introductory examples, go to interface, go to streaming, and we're going to use an array of streams. And we're going to create the HLS template. And we're going to go into the includes. Actually, I want to go into this guy right here. We're only going to do one stream, not 3 streams. And this is just setting these up as an AXI-S interface. We want to, I have some included features that I want to look at. So we're going to go open a file from the other one I have set up. Actually, all the way in here. So this is the one I want to run. We can walk through all the pragmas. So, what we're doing in here is we're doing HLS. We have an input stream, an output stream, a parameter. We're going to call it add val. We're going to set up the streams as AXI-Stream interfaces. We're going to make the add valve an AXI-Lite writable register. And this is also set up the return as a register value as well as the controls. And then in here we have the pipeline, which is going to try to get this to be able to do a initiation interval every single cycle, so you can be fully pipelined. In reality, the MicroBlaze isn't that fast. We probably could set this down to 3 and be able to keep up with the MicroBlaze just fine. But this is what we're going to do for our basic HLS system. Let's go ahead and synthesize this and get it up and running for our system. So SCU35P. That one. Put this down to 200. That's fine. Do Vivado flow and run. So this is going to be generating the HDL code for our very basic HLS system. And this is basically the sum right here is going to return the sum of every 10 values based on this inner loop right here. And M is 1, so the outer loop doesn't really matter. So the synthesis finished. The report is actually super useful. This tells us that we are building for Spartan Plus, that we are able to achieve a 2.4, so we could probably push this up to 400 megahertz super easily. Let's just see how fast we can run the MicroBlaze at. You can look over here what utilization. This is a really simple. We're only using 140 and flip-flops and 279 LUTs, and a lot of that might actually just be built for the AXI control system. We have an AXI light system right here. Oh, where's the control registers? I'll have to app return, app block. Oh, didn't do the return value like I expected. Do I need to, let me do we need to rebuild this with the no control? Now I'm curious. Let me look up real quick on the HLS interface, no control. So we want to use app control no block level I protocol. Okay. Now let me see if I can find an example of this and I can show it. Okay. We want to try this. Let's see what this does. So there's different ways you can do the controls. You can do the controls through ports. You can do the controls through AXI values, or you can do the control through the system. Okay, let's see what happens with this. Okay, I think what I want to do is put this here, and that acting a little bit differently than what I did in the demonstration earlier. So is there software for designing in Verilog and macOS? There's so many different ways you could design with Verilog that, yes, there are solutions for doing Verilog on macOS. I'm not exactly sure. I don't really use a Mac, but there's definitely ways you can do Verilog synthesis on a Mac. Okay, this is what I was expecting right here. Okay, now if we go back, did this. What's this? Out. Okay, so we're going to be using a control register. Okay. So we're going to be doing this method right here. And I'll just demonstrate that we have a control register. Then I can show you what that means in the driver software when you package it. Okay. Now, so in synthesis, we can see the registers. So we have these registers, and they tell us the bit fields. AP start, AP done, idle, restart. Continue. Yeah, I need to learn the ins and outs of these different things. And then we have our AXI input and our AXI output right here. And then we can package this for Vivado. And let me go ahead and open up our previous folder that we had set up. Okay. So when you package it, you go to the HLS folder here, and there's an implementation, and you go to IP, and this is the package right here, the zip that you would, import to Vivado, or you can just reference this folder. But in drivers, you can go look at this is probably the most useful file right here, the x.hardware h file. And this will give you those registers. So right here we have all the registers and their fields, and then we have all the bit values. This one has an AP continue, which is different than we saw earlier. But there's different ways you can implement these interfaces. And the utilization did increase with our system. Okay. So that's kind of the basic HLS, right? So we can go down here, we can run the synthesis, we can run the package. You can also do a C simulation and an RTL co-simulation. And the implementation actually goes through out of context implementation just to prove that the wiring works. So there's a lot of small features you can set up over here. So this creates a block diagram. So we're going to go and then jump to implementing this DUT inside the system. Okay, so go to the IP catalog and talk it through here. So if you're joining us, we're about 30 minutes into the stream. I'm FPGA Zealot. We're doing an AMD sponsored stream. We're looking at the MicroBlaze V RISC-V soft processor and using its AXI-Stream interface to connect to an HLS designed co-processor accelerator. Feel free to talk in the comments, ask questions, provide feedback. We're going to be looking at the full demonstration of integrating the HLS DUT with the MicroBlaze subsystem. So first thing we do is we're going to add the HLS repository to our IP, and then we'll have this DUT. So this block diagram already has the DUT implemented, so I can just show you how easy it is to add it. So right here we already have a DUT. Is there any settings? There's no settings right now set up for it. Might be able to do something fancy. But what we can do here is we can just go add IP, and since we added the repository, we can add another DUT. And then we can hook it up appropriately. Not really hooked up right amount, so let's not worry about it. So here we have the DUT. We've hooked it up to two AXI data streams. These are both, small distributed RAM AXI streams, and they're both connected to the MicroBlaze. So the MicroBlaze is going to write a value over this system, and then it's going to connect it to the DUT, and then the DUT's going to put the output to this data stream, and then we can read it on the MicroBlaze side. We can go ahead and open the implemented design so you can see how much, utilization we're using for all these little subsystems. hopefully this doesn't take too long to open. But thank you. I hope this is a useful presentation that you can see how you can do a, let's say, like a co-accelerator. A lot of RISC-V processors offer opportunity for like custom ISA instruction extensions. And what we're doing here is we're trying to just avoid creating custom assembly instructions and use the, I guess, the assembly instructions already provided by Vivado and Vitis to be able to just rapidly send small little data packets to and from the accelerator. And so I just want to look at, I guess that's what we want. So let's color processor green. Let's color the FIFOs blue. And then color the accelerator red. Okay, so this is the portion of the FPGA we're using. Let's go ahead and report utilization so we can see what's happening here. Oh, we have a great question from YouTube. Is the RISC-V soft implemented on the FPGA? Yes. So the RISC-V processor right here, the MicroBlaze, is a soft processor. This is provided by the Vivado tool. So this is the Vivado MicroBlaze RISC-V soft processor, and it's implemented in the FPGA as, there you go to this view, you'll be able to see it. Implemented as a bunch of, you know, CLBs and LUTs throughout the FPGA. So it's a soft processor. And then we have a question from YouTube. What does the DUT in this demo do? It's mostly a pass-through, like a pass-through AXI-Stream, but the DUT we defined in HLS. The DUT is defined as basically we're reading the stream, we're writing a value to the stream, and then we're just collecting what our inputs with. So we have an AXI-Stream input, an AXI-Stream output, we have an AXI-Lite input, and an AXI-Lite output. So we can look at all the different options that we have on the system. So that's kind of what the DUT is doing. We have a great question from YouTube. Nico asked, what's the pros and cons of using or not using AXI DMA for AXI-Stream interface? So DMA is really useful, but we need to have a good external memory. I could use like a BRAM example and show like loading data into a BRAM using a DMA from the BRAM to the accelerator and then back to the BRAM. But this idea is that if we're just doing some like simple acceleration, or we're doing some simple like processor accelerator function where we're just going to get like one value out, this is, since where all the data processes is happening in the processor, and there's not a need for a large read or write to the BRAM. You can also use this as the MicroBlaze could also be put into like an AXI-Stream and try to do processing on an AXI-Stream while it's in flight. Maybe we're doing header decoding with the MicroBlaze, and the MicroBlaze is doing packet navigation, where it's going to read a header packet. It's going to create the destination for the AXI-Stream packet. So maybe we're only reading a portion of the AXI-Stream packet, and then the MicroBlaze renavigates that packet to a different destination or something like that. So yes, DMA is useful. Our system's a little small to take advantage of a DMA. It's much easier just to use the MicroBlaze. But there should be some really useful small functions that we can use as like a custom instruction. We're basically going to be emulating a custom instruction within the MicroBlaze and not have to set up a DMA interface. So I guess back to this picture. So what we're going to do now is we're going to go open a recent workspace. So we're going to load this design into the FPGA, and we're going to monitor the value changes between the input and the output and see how the DUT modifies the values. So in our example, let me open up the software for this. This is our add value, right? This is the add value that goes into the .hls. This is start. And what we're going to do is we're going to write a value, we're going to read a value, we're going to monitor for the done, we're going to monitor for the sum. But right now we'll just do that, and then we'll print it out. Let's also go into our settings, right? And we're going to go to optimization 03, and we'll let it build. Okay, we got a question from YouTube. Could you also create a project that uses AXI-DMA? I'm working on UltraScale Plus, MP-SOC. I'm having difficulties reading from and writing to the SD card. So you want to look at AXI-DMA. What's a good source for AXI-DMA? Yeah, I'll look into that. I have some video DMA projects coming up in the future that could be really useful. There could be I'll try to think if we can get DMA working. That might be a useful example of converting from AXI Lite to DMA. We should have enough BRAM. Let me see. Do we have enough BRAM and utilization? Yeah, we have enough BRAM utilization, so I can demonstrate like an AXI Lite DMA, or I can do AXI DMA on this FPGA, I think, with the available BRAM and the system. Yeah, so we can try to do AXI DMA next time. I can probably set that up. Going from AXI-Stream to AXI-DMA. And maybe we can do a D filter. Yeah, we can try something. That's a good question. So yeah, we'll look at AXI-DMA next time. So we have a great question, or great comment from Twitch. So from Kim Possible, do you have any advice for how to debug systems that merge code and HDL? My experience using Petalinx and HDL has been that there are so many layers that even simple problems quickly become major time sinks to debug. That is a difficult issue. So especially we got like a soft processor, you have software, you have HDL, a kernel, application code on top of that, plus like user interface, right? There's so many layers that you potentially have a problem that you have to resolve. And that comes down to probably like system modeling, doing proper simulation between the different layers, creating like requirements, trying to define how these different layers interact with each other to decrease the potential for bugs. And that's why a lot of systems are really, really complex. Of like, sometimes it just takes good planning to reduce bugs rather than just like coding. I would love to look at some open source system modelers and how you can use that to help look at these multi layers in your projects. I need to go search for that and figure out how you can use that effectively with FPGAs, soft processor and hard processor systems, plus the external ICs of memory, ADCs, and DACs and whatnot. I think it'd be interesting. Another question from YouTube, is DMA direct memory access? Yes, so DMA is direct memory access. We can drop something in here real quick since we already built this design, so let's do that. You want to talk about DMA, so we're going to do direct memory access here. Let's double click this guy. We're not going to do scalar gather, let's do a micro DMA. Okay. And what a good example of this, we'll just kind of do this like a separate thing, right? So we have AXI-Stream, we'll loop this around. Then we're going to create a memory controller, right? VRAM in this one, AXI VRAM controller. Drop this down. Do these. Okay. So, and then we're going to do a connection. We're going to take our VRAM controller, we're going to connect it to our DMA. And connect this to our VRAM controller. Okay, then let's add a dot here. So here is an example of, see if this is help, kind of. So here's an example of using DMA instead. So instead of using AXI-Stream of a processor, what happens is we're going to connect this. Go ahead. Yeah, we can go to do that, I guess. Connect that to the processor, right? So what happens is the processor here would then define this direct memory access. Direct memory access would go and do read transactions from the DRAM, send it out the stream port, go through the DUT, then go into this FIFO, and then go to this memory access and write it back to the BRAM. So this is something where you can load from the BRAM, go through AXI-Stream in the DUT, and then write back to the BRAM. And we're not going to be using the processor to do every individual write. We're going to have burst transactions of the BRAM. This would be really good for like data compression, data encryption, something like that, or JPEG decoder or something like that. There's lots of little applications for that, but there's more setup and getting the DMA controller set up. We got to load the BRAM, and since the RISC-V is going to be loading the BRAM anyways, there's not really good use in this application. We probably need some like SD card or Ethernet. We're going to be downloading data directly to the memory and then DMAing it through the accelerator, not going through the processor. You don't want the processor doing a majority of your data handling. You want your subsystems to be moving data between each other. Okay, I think I've answered all the present questions. So there's our AXI-Stream DMA. Maybe we can do that next stream and talk about that setup. So the AXI FIFOs can be VRAM. That's a really good question. So in this AXI FIFO, we can do distributed RAM or we can do block RAM. So the FIFO can be VRAM. I'm doing really small FIFO, so I'm doing distributed RAM, which is just using LUTs and just using some flip-flops and LUTs within the FPGA and not a full VRAM. But yeah, it can be VRAM. Doesn't have to be. It can also be URAM in the bigger FPGAs with the UltraScale Plus family. There's a new memory type called URAM. Okay, so we kind of explored this a little bit. Let's go ahead and look at the accelerator in action. So we're going to be triggering off the output of that value. So our code, we're just going to start it, and we're going to write 10 values, read 10 values, and just demonstrate how that works. Okay, triggered everything. Let's run. Get the tera term up. Okay, clear the screen. Okay. That is the old system. I did not program it. Okay, so let's go reprogram the FPGA. Forgot to program it. Is it loading up here? Yeah, it's loading the right one. Okay, so let's trigger on this again. And clear the buffer and rerun the program. Run. Okay. Great question from YouTube, from Nico. Is it using the AXI control interface on the HLS IP? You can definitely turn it off. It'd be interesting to do some variations of the AXI control. I was having some synthesis issues of my HLS system, so I think I need to look at rebuilding different HLS cores where the control is external, the control is internal, the control is off. I want to look at the different control interfaces. But I think you don't need to control. When you're doing AXI-Stream, you can just keep using the data. So these, my mouse here, right here. So here's our return values. We added 100 hex to each value. Let's go look at that in Vivado, probably the most interesting thing. And this is a little slower because we're doing a read write and then we're doing other AXI transactions. But let's try to make this a little quicker, right? Let's go to program device again. Rebuild the code. I want to rebuild the code. So let's take this out of the loop. We'll build that. Let's go ahead and trigger. I want to show you it working a little faster. Okay. So we're not going to be doing a bunch of the reads. So to get effective code here, you're going to want to kind of not slow down the process of other extra reads. So here we're able to do a bunch of different. We're not doing the extra style in, style out. It's mostly I wanted to demonstrate this running much faster. So we can go input, output, input, output, input, output, input, output. We don't really see. We didn't really change the value, so you don't really see it, but it goes much faster, right? We can do this every few clock cycles. Okay. So next I want to show you, we can change this value to 200. I want to show this externally right here. So this is just going to show the sum. It's going to be what, 16. Why this is building. We had a question from YouTube we can talk about. Oh, we don't want an I there. Build that. So we had a question from YouTube. Which UltraScale Plus FPGAs are suitable for learning memory design? It matters what memory design you are thinking about. If you want to learn how to write like a DDR3 or DDR4 controller from scratch, a lot of these FPGAs are built to use like hardened I/O systems to be able to run at like the full operational speeds. Those are very, very difficult. Those are very, very difficult to get up and running. If you want to look at HyperRAM or SRAM, any of the FPGAs probably have some good examples of how to hook that up correctly. But a lot of times you're going to be using the built-in memory interfaces that are provided by Vivado. So I don't know what you're looking for in a memory design. But if you want to learn how to use Vivado solutions, any of the FPGA should have like any DDR3 or DDR4 FPGA will have that built into the Vivado block diagram so you can interact with the DDR. Okay, so right now we're looking at the sum value right here. So 10. And we're only sending 10 values. We changed the add value to 200 hex, we can see, and then we're going to add it together. So now I wanted to look at the auto start feature. This is going to be auto start plus start. Let's go ahead and set this up to like 51. And go ahead and that off. Build that. And the print statements are going to make this terrible. We're only going to see like one value here. But I just wanted to show how this updates. Okay, so the sum value is updating every 10. So every 10 it's redoing a sum. here. And then we can see the output values of all these. This is the first 10, the second 10, next 10, after that, and after that. So it's really easy to build an interface here that then is going to act on the data. I want to do some examples, some actual useful accelerators, so you can be able to see how you can like use this for playing around with a HLS accelerator, play around the tools to figure out how to use it appropriately. And then we can look at hooking up to like an actual DMA system, where if you have data in flight or large memory, you can DMA large memory rather than having the processor, do every single line. I think this is a good way to play around with the system without committing to a lot of extra structures. And here you're only going to see the one because you have the print statement there. Yeah, I think that's what I think that's about all we can really demonstrate today. Oh, the base address. So we should probably talk about the base address here. The base address is 10,000. If you're new to Vivado, you can go to the IP integrator. You can go to address editor. And here's the base address defined right here that we're using. And then we're adding these offsets right here to go to those other registers and use those values. Okay. Thank you for all the questions in chat. So next time we can look at DMA. I do want to look at high-speed interfaces, so maybe we can find a way to provide real-time data and then use that DMAing it to a source, but we might have to just do DMA and BRAM. So maybe just a DMA, so like MicroBlaze with AXI DMA. How do you do the AXI DMA? How do you play around with it? We could talk about some of those examples. Any other suggestions for future FPGA streams, whether AMD or other? But DMA seems like a strong question where we can talk about how DMA works and dig into a little bit more down to the technical details, I guess, of the DMA systems. Because DMA can get complex. We can do very simple DMA, but there's also, scatter gather, which is using kind of different pages. You would use scattered gather when you're doing like virtual memory support, but that is way more complex when you would have like a Petalinux subsystem. But right now we're kind of focusing on smaller embedded examples. So thank you for joining. I'll keep you posted on future streams. You can watch the recording of this stream on YouTube, Twitch, or LinkedIn. We'll have future postings. I'll probably be looking at doing a video this Saturday and another video Tuesday, and then we'll be off for Thanksgiving until December. So probably 2 more videos for November, and then we can see how many more videos we can get going off in December. But join the Discord, leave a comment, like, repost, subscribe, whatnot, to keep up with the different videos I'm going to do. Feel free to come into Discord, ask questions, ask examples. I can provide more information. And hopefully we'll have some GitHub examples and articles coming up in the next month or two that you can follow off. You can follow without directly watching a video. But thank you for joining us. This is great to watch. But yeah, feel free to leave any final comments. I'll stay on for a few more minutes. But yeah, it's great if you leave a like. It would help share this. But a lot of times this video is just being able for someone to find something useful through the search. It helps a lot as well. See. with that. Okay. Good comments from Twitch. Sorry, Evan, I didn't say hi to you earlier, but thank you for joining the stream. I think that's about all. Okay. Since I see no other comments at the moment, thank you all for watching. Join us on the next stream. Have a good day. Bye.